Okay. All right. This is lecture 11. And please pardon me today. I've got a bit of a cold, so you'll just have to bear with me there. Today we're going to talk about the Krog tissue cylinder. Oops.
And we're also going to figure out how this... Oh, come on. Okay, I might
let's
restart
start
this
over.
one.
Yeah, all right.
Okay.
And am I ready to write? Yeah.
Yeah, cool.
Okay, so this is lecture 11, and please bear with me today because I'm enjoying a cold, so I apologize in advance if I cough. We're going to talk about the Krog tissue cylinder, and we're going to look at the example. We're going to look at the concentration profile equation for that we develop, and a few other things. We'll get into that. Okay, let's just jump into it.
Yeah, today we are going to be tired and imperfect because sometimes that's what happens and it's okay.
Okay, so we're looking at flow through this capillary here, and a solute, any solute, let's say it's something that's being consumed by the tissue, is diffusing out of the capillary and into the tissue. Okay, although I loved the comment from one of the students in class that it could be the other way. Maybe it's something that's generated in the tissue and diffusing into the capillary. It works either way. But for today, let's just consider that it's moving from the capillary into the tissue and being consumed in the tissue. The capillary has a radius of r sub c. The capillary wall has a thickness of T sub m. So the radial distance at the outer edge of the capillary is Rc plus T sub m. The blood is flowing at a velocity capital V. And the radius of the entire package, including the tissue and the capillary, is R sub T. Z is our axial distance, so Z and Z plus delta Z. And then, of course, R is the radial distance. So we're going to be looking in both directions, the axial and the radial.
So, cylindrical coordinate system, I take it.
Yes, of course. And also,
Gotcha.
Also, this example is given in some material that Dr. Babansi posted on Canvas here, so you can go back to the original source there.
You don't have to, but you can.
Yeah. All right. So these are the assumptions. We're going to look at the tissue as if it's just a continuous phase. Forget that it's, cells and so forth. It's just a continuous phase. And we have an effective diffusivity d sub t for the tissue.
So it's a cylinder of stuff, like homogeneous stuff.
Right. We're going to assume that the consumption, it could be production, but we're considering consumption, follows the Michaelis-Menten relationship. Actually, we're going to assume that it's a constant.
Okay. So how much of a simplification is that?
That assumes that it's a value over the concentration plus another constant. And so it assumes that the concentration is larger than that constant. It's, it depends upon what the solute is that we're talking about.
But it can be a decent approximation for something. This isn't like stick figures.
Yeah, it's a decent approximation.
Okay.
If you wanted, it's the only one we can have to get an analytical solution. If you have a different rate equation, then you can't make an analytical solution, as far as I know. You'd have to go maybe to MATLAB or MathCAD to do this. Okay, so the solute is transported out of the capillary, or actually what they're talking about here, the solute is transported primarily by convection in the axial direction. What that means is that the solute is being convected down the axis of that cylinder
So through
by
the
the blood flow.
capillary.
Yeah, through the capillary by the blood flow. And then in the radial direction, it's diffusion through the tissue. Let's see. Diffusion of the solute from the blood and through the capillary walls is proportional to, is proportional to the concentration difference. So it's just a very simple equation. It's the difference in concentrations times an overall mass transfer coefficient. And then this overall mass transfer coefficient, combines the resistance of the convection and the permeability of the capillary wall. We're going to treat the blood as a continuous phase and well mixed too, by the way. And this we know. Okay.
Okay, so it's a pretty simplified model for everything is homogeneous, and we ignore the fact that cells exist and have shapes and sizes and bump into things.
Right, but we've simplified it quite a bit.
And that's okay.
Okay, you know what? Before we jump into this, let me go back here and talk about the equations that we're going to be doing. I need some space here.
Do you want to let me erase you a bit?
Erase this little bit here. Sorry.
You get to see our production process.
Okay.
And
Oops.
I gotta turn you back to the pen. And someday we may have fancier software, but today we don't.
Okay, so we're going to be doing 3 different equations. We're going to derive 3 different equations. The first is a mass balance. And if I recall, the mass balance is... What's the first one? It is... Okay, so the first one is a mass balance on our solute in the blood. And it's going from Z to Z plus delta Z. Okay, so the first mass balance is in the blood. The second one is a mass balance on the solute in the tissue. And this is going to be at any value of Z, and we're going to go from R to R plus delta R.
Okay, so at some distance Z with the blood flowing along the capillary, we're still varying the radial
Right.
dimension.
Right. And then finally, the third one is actually the same as the first. It's a mass balance on the solute in the blood. The only difference is we're going to go from 0 to some value of Z. Okay, so it's exactly the same as the first one. It's just we're going from 0 to Z. And basically what this is doing is this is giving us a boundary condition.
Yay, boundary conditions.
All right. Excuse my cold. Okay, so this first one is the mass balance on the solute in the blood from Z to Z plus delta Z. And so what we have here, this is the solute that's being brought in by the blood coming in. So this is the velocity times the cross-sectional area times the concentration.
Oh, yeah, pi r squared, yeah. Okay.
Okay, so that's in at Z, and this is out at Z plus delta Z. Okay, so input minus output, and this is the rate that it is exiting by means of convection.
And where do you get that from?
Okay, now look at this. Just let's just simplify it. We'll look at K0, and for the moment, let's pretend that that's just the convection coefficient. There's more to it, but let's just simplify it in our minds right now. So it would be the convection coefficient times some change in concentration times the surface area, and this is the surface area. 2 pi RC is the perimeter, and delta Z is the length.
Oh, okay, so it's the cylindrical sheath
Right.
surface area.
Right. Okay, so that K0 is an overall transfer coefficient. So it accounts for the convection resistance and the permeability resistance. We spoke about that in lecture 8, I believe. And I'll just write it here. 1 over the overall is equal to 1 over this is the convection, plus 1 over the permeability.
And lecture 8 was the one with about membranes.
Right.
And if you think about that, and you think about if you've taken circuits courses, this is how you would add resistors as well.
Right. Okay, so that's what that overall mass transfer coefficient is. All right, so we have done a little mass balance here, and rearranged it to come up with this lovely differential equation. All right, now by the way, let's see, this C here is the concentration in the blood. C bar is the concentration in the tissue.
Is that a standard convention?
Not to my knowledge.
Okay, it just happens to be what we're
But
using here. The C bar is tissue.
Right, it works here. All right, so that was the first one. Here's the second one. Let me just put a 1 there. So that's the first one. Here's the second one that we're going to do.
That's a really helpful label for me, by the way, because separating them give my brain a little less to do now.
Okay, so we're going to look at a mass balance at a given value of Z, and we're going to go from R to R plus delta R. Okay, so we're in the tissue, and by the way, we are neglecting any diffusion in the axial direction. Okay, because if we took account of that, we couldn't get a nice analytical solution, and it's probably pretty negligible anyway.
So, in English, for my brain, that means that we know that there's blood flowing through this capillary. We know that it's moving, down through the capillary tube. And so there is some diffusion kind of also going in that direction of the blood flow, but we don't care.
In the tissue, okay, for the second one, we're in the tissue.
In the tissue, there's probably some little bit of pushing along.
There are concentration gradients in the tissue in the axial direction, so there is diffusion. If there's concentration gradients, there's diffusion. But in the axial direction, it's not as great as in the radial direction, so we're going to neglect them.
That makes sense.
All right. Okay, so what we have here, this is, okay, now we have a little shell. First, let's imagine our shell. It's at some axial distance Z, and it's at radius R within the tissue. And it is going all the way around, so its perimeter is 2 pi R.
It's a cylinder.
It is, but not this cylinder. Can I erase? You're really close.
I'm really close. Okay.
Yeah, it's this cylinder.
Oh, it's a very, very small.
Well, actually, yeah, because we're at some value of z.
So it's just delta Z long.
Yes, it's just delta z. And it has a radius of r.
I've had a really long delta Z.
No, we're just at z. So, and I need green again.
Yeah.
Okay, so this term is diffusion into our little shell. Oh, and by the way, I'll put blue on. By the way, it is delta R thick. So here's our shell here.
So it's like macaroni. Like a very, very small piece of macaroni.
I guess. Or a ring. It's like a ring.
A ring.
Okay, so this is diffusion into, oops, excuse me, not that way, in the R direction into our ring. And this is diffusion in the R direction out of our ring. Okay, and this is the consumption. Now this R of C bar, meaning it's a function of the concentration in the tissue. But later she's going to just say that it's a constant R0.
And that's the reaction? That's the consumption?
That's the rate of consumption per unit volume.
Okay, and I will note that for my own brain, remembering that that's the rate of consumption and not a radius.
Yeah.
I have to think and be like, that's not the outer radius of something. It's a different R. It's a different R. So I might use different variables or label it somehow to decrease my cognitive load that way. But this is how it's written here.
Right. So this is the reaction rate, and it's per unit volume. So this is the volume of our ring. Okay, so it's the distance around 2 pi
R delta Z.
Oh yeah, I could barely see it in there, but there is an R there. Okay, it's 2 pi R delta Z is the volume of our ring. All right. Sorry for my cold. Just bear with me.
No, good.
Okay. Now, if you play around with this, and I do encourage you to look at the notes that she posted to derive that, then you get this lovely and beautiful equation for the concentration in the ring as a function of R. Okay? At a given Z. Oops. Okay, now she's got some boundary conditions because what she's going to do is integrate these equations. Let's look at these first two here because this is what she's going to do first. First, she's going to integrate, she's going to integrate this equation in the tissue, and she's going to use these second two boundary conditions. And let's look at them. At R equal R sub C plus Tm, so we're on the outside wall of the capillary. So we're in the tissue, so we have C bar. And she just said C bar is equal to C bar at RC plus Tm.
Can I redraw a cross-section
Yes,
real
please.
quick? So one of the strategies that I've done, by the way, is if I can reduce my cognitive load in any way, it helps me use the rest of my brain to focus on the problem. So we have R sub C is the inside.
Radius of the inside of the capillary.
So that's R sub C. And then
There's a thickness of the capillary.
and then this is T sub M.
Oh, okay.
And then, so the two of them combined is the entire new color, entire distance here.
Right.
Okay.
Yeah. And by the way, just to be complete,
Back to you.
way out here, oops, it's not writing. Way out here, somewhere, is RT.
Okay.
Okay? All right.
Of the tissue.
Yes. So the tissue is here. The capillary is in the blue.
And the tissue is in green.
And the tissue is in
because we're not using actual colors of biological materials. We dyed it. There's a lot of dye involved in this.
It could be plant tissue.
It could be.
All right. Let's see. So what she does is to use these two boundary conditions. And this one, it's not really a boundary condition. She's just giving it a name. And so what we're going to do is later we're going to make up for that with our third mass balance to get a boundary condition. She doesn't say that, but basically that's what she's doing. All right, so she does that, and her notes explain it very well. And now she has this equation. It is a function of R because we integrated it and came up with R. But it's also a function of Z because of this term here, which is a function of Z. This is the concentration in the tissue right up next to the wall, outside of the capillary. And that is a function of Z.
Oh, because the blood is moving by convection inside the capillary?
Yes. Well, because the concentration of the solute in the blood decreases as you move down the axis because it's leaving.
Because it's being taken up by the tissue, so there's less and less of it as you...
Right. So since there's less in the blood, then there's less in the tissue right up against the wall.
That makes sense.
Okay. And then she states we don't have the information about the C bar at the wall in the tissue. So that's why she does this next mass balance, and this is number 3. It's actually the same as number 1. At any Z, we're going to do a mass balance from 0 to Z. Okay, so this is what's entering at Z equals 0. So it's just the velocity times the cross-sectional area times the concentration that's coming in. And this is the same thing, only exiting. Okay, actually maybe I should draw it. So we're looking at the blood.
Mm-hmm.
Here's the capillary. And it's going from 0 to L. But we want to go, pick yellow, we want to go from 0 to some value of Z. Okay, so we're going to be looking at doing a mass balance about that volume there. So what comes in at this point, so what comes here, in here is given by the first term, and what leaves here is given by the second term. Okay? And then the difference between these is just how much, how do I put this? How much is convected out, but also since it's a steady state, what's convected out is equal to what is consumed in the tissue. Okay, so there's one little extra step there. All right, and what's consumed in the tissue is that cylinder of tissue. Well, let's start here. Here's the reaction rate, and times the volume of the tissue, which is the cylinder of the tissue minus the cylinder of the capillary. Okay, so it's
if we go up to the picture a little higher up, it's come on iPad. Okay. It's this green section over here.
right. Okay, so it's the cross-sectional area of the green minus the cross-sectional area of all of this. I completely destroyed that. Let me take that off because it just looks hideous. All right.
I already have ideas on how to redo these videos next year, this summer.
Okay. So anyway, it's pi r squared times length is the volume of the cylinder. So it's pi r squared for the tissue cylinder times z is the length, from going from 0 to z, minus the same thing for the distance to the wall, to the outer wall.
We've got in our little diagram up there, right here.
Yeah.
Actually, that should be in yellow. Pretend I did that in yellow the first time. And back to green.
All right.
Oh, no, wrong button, not that one. Oops. There we go. Okay, bloopers.
All right. So just rearranging that, we get this lovely equation. How do I get that out of the way? Lovely equation right here. Oops. Hang on.
And yes, we will be. Oh, come on. Here we are.
Thank you.
You
Okay.
are getting very, very tired people today.
I have a cold, so you have to forgive me everything. All right.
I think it's good to show that we are also humans.
So basically, this equation we're going to use in order to get rid of, or actually to find what is the concentration in the tissue at the wall as a function of z. Okay, so once again, Dr. Bavency posted her notes for this, and I really suggest that you take a look at them. And basically all she's doing, it looks complicated, but all she's doing from this point on is she's combining the three equations that we talked about.
The
1, 2, and 3.
the 1, 2, and yeah, I really need to get better software for this. 3, which was you also pointed out in an earlier slide. This stuff here.
Right.
So just connecting ideas across slides here.
Uh-huh.
Do,
So-
do, do, do.
So then there's some algebra in a little bit of calculus in order to come up with the final equation here. So this is the concentration in the tissue as a function of R and Z. And you can see it starts off with the concentration of the blood, but it's decreased in terms of, because of the reaction, it's decreased, because not only the reaction, but the convection resistance, and it's decreased because of the diffusive resistance, and again, the diffusive resistance. Okay, so it ties everything together. And now she says, in looking at this, the solute the delivery of it can be limited by the capillary flow rate, which is determined by the velocity. So if the velocity is low, then this term is larger and it's negative, so it decreases. It may be limited by transport across the capillary, which is this term here. If K0 is, if K0 is very low, very small, then once again this term becomes large, and it's negative, so it would decrease the transport. And then if consumption is rapid, then all of these negative terms are increased because R0 is in all of them. Okay? And now she's kind of having some fun with it. Basically, she's taking some value of RT. Remember, RT is the outside diameter of our Krog cylinder. And she's saying, okay, if I take it large enough, then my concentration, C bar in the tissue, is 0. I'm going to call that R critical. Where is it? R critical.
Okay, so I'm just translating this into pictures in my head where you've got a capillary of blood flowing through it that has something, I don't know, glucose or...
Yeah, glucose.
Sure, glucose. And it's diffusing out of the capillary into the tissue of, let's say, my arm.
Okay.
But the capillary is really small, and I have muscles that are larger. And so if I only had that one capillary, there would be a point in the muscle that would be too far away from the capillary for the glucose to reach.
Right, right. And so all she's doing is taking this equation here and setting C bar equal to 0. And then all these RTs become R criticals. And let's see, all of the R's? Yeah, even the R's become R critical because that's where we are. We're at the critical radius. And she gets this crazy looking equation, which is not as bad as it seems. That's all she did. That is literally all she did to get that equation.
Okay, so it's just a lot of variable substitution.
Actually, no, just C bar is 0 and set R equal to the R critical. And also RT is the same as R critical. That's it. That's all she's done.
Okay.
And now, if you want to find the value of R critical, it's implicit in this equation. You would have to, I don't know, trial and error. Or, you know.
And actually, if I throw that back to my fabricated example of the capillary bring glucose to the muscle in my arm, this equation would help us start thinking about things like, well, this is why you have more than one capillary in your arm, Mel. How close together do your blood vessels need to be?
Unless you have very skinny arms. Okay, and this example, all she's doing is she's putting in values here.
So it's the same thing, now with code.
Yeah. Well, very simple code. So here's, she's giving us values for diffusivity in the tissue. All of this, let's see. She's doing a little bit more here. She's calculating the Reynolds number, calculating the Schmidt number, the Sherwood number.
And all these things are a combination of, we looked this up in a book for you somewhere, and then did algebra.
Actually, you have the tools to do all of this. The reason they did that, yes, you do. This came from that table of relations between Sherwood number and Reynolds number and Schmidt.
Oh, was that the lecture that you did on
Yes.
convection? That was lecture.
That was the first convection lecture. And it had a table of those relations. And so that's all we're doing. So you could calculate this.
But now you don't have to because she did that for you.
And so once you know the Sherwood number, we're going to use the Sherwood number to multiply it times the diffusivity, divide by the diameter to get the mass transfer coefficient. She's giving you the permeability, and so now you can find the overall mass transfer coefficient. Let's see. This comment, by the way, relates to that. It's kind of upside down. Anyway, so first we're going to use one of our relations to find the concentration in the blood. then we'll use this one, to find the relation of the concentration of the solute in the tissue, but right up against the wall. And then we just plug that in to find the concentration in the tissue as a function of C. And, actually, no. This is the concentration, not just in the tissue, but at the very edge. Okay? So it's at R sub T. All right. So these are just the equations that we derived. That's all those are. Then she plugged all the values in, and she found this is the concentration in the blood, and you see it's decreasing as we go down because it's being diffused out. This is the concentration in the tissue at the wall, so it's this line here. So you see it's less than what it was in the blood because there's a resistance between the blood and the tissue right up against the wall. And then this one I find very strange, but this is the concentration of the glucose at that outer radius. And it, as far as I can tell, it's right up here, right up against the same value as was at the wall.
And this all makes sense because, right, as the blood gets further down the capillary, it's gonna decrease because it's getting absorbed by the tissue, and so similarly the amount in the tissue would go down in a rate that matches that, but because it's diffusing into the tissue, there's less of it there than in the blood.
And in this case, maybe I should get rid of it, what I drew in there. In this case, the concentration at R sub T is almost exactly the same as the concentration right up against the wall, and I guess that's because maybe glucose is has such a high diffusivity. Perhaps I'm not sure.
I don't know. Is that the substance that they put? Yeah, it was glucose.
Yeah.
Oh, I was not thinking about that when I made up the capillary glucose in my arm thing, but.
And R sub T for the capillary may be set up for something that's not as diffusible, if that's the proper word.
Lower diffusion coefficient?
Maybe oxygen has a lower diffusion coefficient.
Diffusivity.
Thank you.
Diffusivity. That's the words are hard. Words are definitely difficult. And especially if you are coming to this as a non-native user of English, the distinction between diffusion, diffusivity, that can be difficult.
Even if you just have a cold. Okay, so anyway, that's what happened there. And now she's doing the same example, only she's just plugging in 0. Let's see, 0. Yeah. She's using this equation where she plugged in 0 for the concentration and had it find the root of that.
So that's the critical radius that we talked about in the example of glucose and the muscle in my arm. This is the point where the muscle isn't getting glucose from this capillary. So we kind of hope that there's another capillary nearby.
And well, this is just interesting. It's just an interesting application here, that the critical radius as you move downstream. So let's see, the critical radius, we started with 40, and 40 was fine, but at some point, that's very small, around 0.02, I think, the critical radius decreases below what is actually the radius of the tissue, which means that tissue in this area here, or actually tissue in this area here, is not receiving sufficient amount of the solute.
So that's the muscle that's not getting glucose.
Right.
And again, that makes sense because as you go further down the capillary, there's less glucose in your bloodstream because it's been absorbed by the muscle before it. So once you get to the further downstream, the muscle is like, "Hi, we like glucose," and the bloodstream is like, I'm sorry, I gave it to all of the tissues before you.
Well,
Good luck.
hopefully we don't have much or any of this problem in our circulation. But it could happen,
Yeah.
I guess.
I don't know. I had a long rowing workout last week, and so I was definitely starting to feel some of that. But
That's
yeah.
the lactic acid that needs to leave. And here she's just talking about where we got that overall mass transfer coefficient. And it starts with this expression, but I don't think you need to worry about how to get to that. Just realize you're adding up the resistances this way, the inverse of the resistances.
And note that this slide is called an aside. And that and the critical radius stuff it's just for fun. If you're studying for the exam, do not prioritize these things. But they are cool.
Let's see, and yeah, this is okay. My partner here is suggesting that we've gone almost as long as the entire lecture, so I think we'll call it quits here. This is basically, actually, she stopped here in the
Critical
lecture.
radius stuff.
Yeah.
It's so to recap. But I mean, this is fun though, right?
Yes,
So what did we do today?
Well, we looked at a way to find a concentration profile, the equation for concentration in the tissue surrounding a capillary.
Or some other kind of tube. It could be. It doesn't have to be a capillary.
Yeah, I guess it could be something else.
I'm thinking about like in terms of equipment. It might be, you're doing some kind of waste treatment thing. And so
could
stuff
be.
is flowing down a pipe, and you're like hoping that the photos around it would do things to that.
Right. This second part is what she did in lecture on Thursday, and so perhaps we can.
Yeah, but we'll do that one later.
Yeah, we'll do that later.
But the thing that we modeled with the, here's your capillary, pictures, whoops. I don't know, I did this in the wrong order. Capillary, and then tissue around it. This is the Krog
cylinder.
Pronunciation's hard. Krog
cylinder.
tissue cylinder.
Uh-huh.
And so that's sort of like a standard model that you'd see and use.
Most people in biomedical occupations or modeling would be familiar with it. Yeah.
Okay, so if you walk around an apartment talking about the Krog tissue cylinder, everyone's gonna be like, "Oh yeah, the Krog."
Maybe half of them.
Half of them. But that's actually good to know too, because I never know which things are gonna be common parlance and which ones are.
Mm-hmm.
One person knows it because that was their thesis.
Yeah. Well, it's a very nice example that involves not only diffusion but convection.
That is a nice combo. And we have lots of blood, we have lots of stuff being transported in blood, so that makes sense. Alright.
Okay.
Let's call it a day.
All right.
Good luck, folks.